Hi everyone. Let's talk a little bit more about Earth science and let's continue with the discussion of the Earth's interior. In order to understand what's inside the Earth, first we need to talk about seismic waves, vibrational waves that travel through the Earth. And it turns out there's two types, and we've seen these types of waves before. They're just going by different names. In Earth science, there's something called P waves, which stand for primary waves. Those are the longitudinal waves that we saw before. Back in the physics section, those are the compression expansion waves. And then there's S waves, also known as secondary waves, but we studied them as transverse waves, normal waves that kind of go up and down. Now the S or secondary waves are actually slower than the P waves. Well, they both have S's in them. We'll remember it that way. And turns out that the secondary waves, the S waves, cannot travel through gases and liquids. And then you might be thinking, wait a minute, I thought transverse waves happened in water. Well, on the surface of water they happen. And that's because the weight of the water can pull the wave down. But if you're inside a lake or inside a swimming pool, you can't create S waves, transverse waves. They don't propagate through water. Okay, here's a quick review of transverse waves and longitudinal waves. Our longitudinal wave, that's right here. This is a hammer. And it's striking the bottom of this column of bricks, let's say, or a section of the ground below us. And as you strike it, there's a region that gets compressed. And that compressed zone propagates upward, and behind it expands again. And it just moves on up to the top of the column of bricks here. We can take that same hammer and smack it alongside the edge of the column of bricks and create a wave that will propagate upward. And those are the S waves. Okay, using an understanding of the P waves and S waves, we've come up with this model for the Earth's interior. Starting at the surface, we have the crust. It's a really thin layer. And then there's a larger section called the mantle. And as you approach the center of the Earth, right before the center, there's the outer core. And it turns out the data says this is a liquefied region. And the S waves cannot propagate through it. And at the very center, there's the inner core, which is solid again. So here we go. Crust, well, you know about that. That's the surface, and it's a hard surface, solid surface. The mantle appears to be solid rock, but under the pressure and heat it's under, it can flow. The mantle can flow. It's still solid, so maybe you think more about something like silly putty or modeling clay, how it's a solid and can still flow. And like I said before, the outer core is liquid, the inner core is solid. Okay, how do we know about the Earth's interior? Well, if you have some type of vibrational event like an earthquake on one side of the Earth, well, you create both longitudinal, the compression waves, and transverse, the up and down waves. And so the S waves, transverse waves, are shown like little waves. The P waves are just going to be a line. The compression waves are a line. And as you move away from that center of the earthquake, the waves, the vibrations are weaker, but you can still detect them. Maybe not with people, but with detectors. If you're close by, they're stronger and so forth. And it turns out the waves are traveling through the Earth. So to get this guy, you have some P waves that make their way to him, and there's also an S wave here shown. He feels both of them. Someone on the other side of the planet, however, will only detect the P waves. And it's true, somewhat offset from the center. And then there's a region where you can feel some P waves that are very weak, and what's happening is that the P waves are being refracted, sort of like light does. So the straw appears to be bent because of refraction, and that's because the light ray changes direction as it changes from air to water. And here's some glass down here, a block of glass, and light's traveling here, and it goes to the glass and it gets bent or refracted, and then when it comes back out, it's bent again. And so that's what's happening as the S and P waves travel through the mantle, and they approach a different material, sort of like light travels and strikes air and then moves into water. As it goes to a different material, it gets bent or refracted. And so there's very little P waves that makes its way in through here, because they either keep going straight or they get bent out of the way. and they're picked up at a different location. And there's a lack of S waves. They all got absorbed by the outer core. Okay, let's talk about plate tectonics, the motion of the Earth's crust. And we begin by saying that the crust and the top part of the mantle appear to be broken into 8 large plates. And, that's the main idea. There's several smaller plates that connect among these 8 plates. But those 8 main plates are moving. They're sort of floating on the mantle, if you will. And the mantle is moving these plates on top of it. There's convection currents that are happening. Remember that from heat transfer? We talked about convection as a way to transfer heat energy through the movement of matter. And most of the time we think about maybe an oven where at the bottom there's a fire or some heating element that heats up the bottom of the oven. The air rises, hot air rises, and then off to the side the cooler air will fall. And that's what's happening inside the Earth. The hotter part of the mantle is going up, and the cooler part of the mantle is coming back down, and that's creating motion right below these plates. And so they start moving. Now where these 8 plates meet, and the smaller plates meet, those are different types of boundaries, and there are 3 types of boundaries. There's also another definition we should be aware of, and you probably heard it before when we talk about earthquakes, and that's a fault. And that's just a thin region of crushed rock that separate the blocks of the larger plate. Okay, let's talk about those 3 types of plate boundaries where those plates meet. 3 types are divergent, convergent, and transform. Now divergent is a separation. And so right down this picture we have one plate moving to the right, a second plate moving to the left. How are they moving? Well, the mantle has a hot spot, it's flowing upward, and kind of pushes on those 2 plates and moves them apart. And the mantle comes in and fills in the gap. So there's new material being created at the surface. Now somewhere else, there's 2 plates that are actually colliding. They're colliding head on, and that's a convergent boundary. And then as they collide, one plate will slide under the other one. And that's called subduction. One plate going underneath the other. And as it goes into the mantle, the heat of the mantle is going to melt and transform this portion of the crust back into the mantle. Okay, and there's also sections of the Earth's crust that are passing side by side. And those are called transform boundaries. So here, let's kind of put all 3 of these boundaries together. Here's a section of the Earth's crust and the mantle here. And there's some new names for different sections of the mantle. We can just ignore that for now. So here, let's start with the divergent boundary. That's where one plate is separating from another plate, and new material is going in to fill that region. And then over here on the left, we can look at this part of the plate that's being subducted underneath this other one, the subduction zone. And that boundary is called a convergent boundary. And then to accommodate the round or spherical Earth, these plates are going to crack, and then we're going to have side-by-side motion right here. So this portion of the plate is moving to the left, and this portion of the plate is moving to the right. And right here, this intersection, they're sliding past each other. That's a transform fault or transform boundary. And here's a map of the ocean floor, and you can see that there's this line here. This is a divergent boundary where the plates are separating on the ocean floor. And you can see all these little lines. I'll highlight one there, and there's a bunch of these little wrinkles, if you will. Those are all transform boundaries. I'm trying to find a convergent zone, a convergent boundary. North America and South America, the buildup of these mountains, that's because one plate is subducting underneath the other, and this plate is going up, and we're creating some boundaries. We're creating some mountains. Okay, final 3 topics. Earthquakes. Earthquakes occur at these plate boundaries, and it happens when the rocks stick and then they slip. So here's a convergent boundary, and as this plate slides under, the cooler rocks up here kind of stick against this plate, and as they stick, the plates keep moving and put pressure at that one intersection until finally the rocks just break. And all of a sudden, the pressure that builds up makes the plate slide forward very quickly, and you have an earthquake. We can also talk about volcanoes. They usually form at subduction zones, a convergent boundary. So as one plate happens to go down, the other plate is pushing up. It's going to relax a little bit as this crust moves upward and relieves some of the pressure. And as you lower the pressure, that gives this hot rock a chance to melt. And so we got a hot spot right here. And it can start to flow upward in the cracks in the earth and make a volcano. A tsunami, they form at subduction zones. Again, convergent boundaries. And here's another diagram of a convergent boundary, a subduction zone. We got one plate going underneath the other plate. The ground is really hot, and so the material being hotter and more fluid, these two plates are able to slide past each other fairly well. But near the surface, especially underneath the ocean, the rock is cooler. And so now it's not so fluid, it's not so hot, it's actually, more like rock, hard rock, and now they're sticking together. And if you look at the plane here, this is pretty flat, this edge of the plate, but now it's kind of puckering up as it's sticking. The plate behind it is being shoved upward, and so this is sliding up, it's bulging up as more and more pressure builds up at this region, right at the subduction zone. And at some point, as these rocks are sticking, the pressure will become great enough to snap these rocks that are holding the plates together, and this section will bounce right out. And as it bounces out, there's going to be an upward force of the water, and it's going to create a huge wave. And that's a tsunami. A tsunami created by an earthquake underneath the ocean. And one more time, here's a diagram. Got the earthquake happening at the fault line, the boundary connecting the two plates. And as the upper plate bounces upwards, snaps back into place, it's create a huge wave. That's all for now. I'll see you in class.